In example 4, we're going to put some of the past 3 examples together, and I'm going to make a slight modification to what the book is saying because the book is lying here. So the types of mappings that they're calling linear mappings are really affine. Technically, you can't translate and be linear. Translation is a non-linear thing. It's an isometry, so it's still a nice map, but it's a non-linear map. So with example 4, what is the actual example? And then I'll point out what the nonlinear part of the example is. We're going to look at the image of the rectangle, and our rectangle I'm going to call, let's keep it the book's notation. I'm going to call S, and it's going to be the rectangle with vertices at -1 plus I, 1 plus I, 1 plus 2I, -1 plus 2I. And the mapping F is going to be given by the rule, let me write it as W. W is 4IZ plus 2 plus 3I. So this guy here is the affine part, but this part is inherently nonlinear. It fails the linearity, addition, and scalar multiplication rule. So just be careful about that. Now, what is this function doing? Well, it's a combination of a couple functions, and I encourage you to read the book for the general overview here. But we can rewrite this 4iz as 4 times iz plus, after all of that, 2 plus 3i. So this part is rotate by pi over 2, because I makes an angle of pi over 2 and it's on the unit circle. This part is then multiplied by 4, or dilate by 4, I should say. Dilate by 4 units, or whatever the factor is. And then this part says then, after doing all of that, translate by 2 plus 3i. So, like when we did the square example previously, affine mappings preserve linear objects. So if we wanted to figure out where the square goes, or another type of linear object, it doesn't have to be a square, we just need to figure out where the vertices go. So let's, so I don't have to scroll down, let me put here, let's look at the image of the vertices. Well, image of the vertices. So we're going to look at -1 plus I first. All right, so I'll do this one in detail, and then we'll just write down what the answers are. So we are going to multiply by I, then 4. So that's multiplying by 4i. What's that going to end up being? I think you'll find it's -4 minus 4i. And then we have to add 2 plus 3i to it. So that's -2 plus I. And then if you do these other ones, you could find that f of 1 plus I is going to be -2 plus 7i. F of 1 plus 2i is going to be -6 plus 7i. And then f of -1 plus 2i is going to be -6 minus I. So to figure out where our rectangle went, all we're going to do is we're going to plot these points. And let's see, it's going to be kind of a big graph of C. So we have to go to the left 6, maybe 7. Let's go 7 each direction. And then I'll plot the points I can see, then we'll scroll up. So -6 minus I is here. Let's maybe use blue. And then -6 plus 7i is up here. And then we have -2 plus 7i, so that's up here. Oh, I guess I didn't need to go so far to the right. That's okay. And then negative 2 plus, ooh, shoot. Did I mess up something? Negative 2, oops, this should be a minus I. Negative 4i plus 3i is minus I. Whoops. Our rectangular shape was not going to be rectangular. Okay, there we go. So negative 2 minus I is there, and then we complete our shape to this rectangle. And if I were to draw the starting rectangle here, maybe in orange, our starting rectangle had vertices negative 1 plus I. It had a vertex at 1 plus I, a vertex at 1 plus 2I, and a vertex at negative 1 plus 2I. So here's S, and here's f of S, which we'll call S prime, the image of S. Now, the claim is that if you rotate this square, I keep calling it square, this rectangle by 90 degrees counterclockwise, so whoop, and then you stretch it out by a factor of 4, and then you'll stretch it out, it'll go over here maybe by a factor of 4, and then you translate by 2 plus 3i, you're going to get this blue guy. And if you sit there and you do those steps, you'll find that that's exactly what happens.